All right. Welcome to the GOCC. Today, we're very happy to have Dorian Smith from University of Minnesota. Before we begin, I want to review the community statement. So we have 3 principles. 1 is that we're all learning. 2 is that everyone has something to contribute. And 3 is that no one has all the answers. So this includes the speaker, the audience members, the organizers, everyone at the seminar. Okay. So it is my pleasure to introduce Dorian Smith from University of Minnesota, who will be talking about sandpile groups of cones over trees.
Awesome, thank you very much. So the question that we're going to look at today is following. Given a cone vertex attached to a tree, is there a way to describe the sandpile group of the resulting graph, denoted cone T? In addition, can we bound it by 2 extreme family of trees, the paths and the stars? So just to give you like a visual of what we're talking about, this is just an arbitrary tree. And then the cone vertex, the graph with the cone vertex would just be this red graph, this red vertex. And you see that it's adjacent to every vertex in the original tree. So you're probably wondering, what is a sandpile group? So to any finite connected graph G, we can associate a finite abelian group called the sandpile group. The sandpile group is the torsion portion of the integer co-kernel of the Laplacian matrix. And this group is an isomorphism invariant of the graph, and it reflects certain combinatorial information about the graph. For example, the cardinality of the sandpile group is the number of spanning trees of the graph. So to calculate the Laplacian matrix, here's an example. We take the degree matrix and we subtract the adjacency matrix. So for this simple graph here, and if we're just kind of showing place setting here. Okay, so vertex 1 has 2 neighbors, vertex 2 has 2 neighbors, and then vertex 3 has 2 neighbors, and then 2 is adjacent to 1. So I put a -1 in both of those spots. 3 is also adjacent to 1. And then 2 is adjacent to 3. So that's how we compute that Laplacian matrix. A little fancier example would be this graph here, where we have the vertices labeled 1, 2, 3, and 4. And so our matrix is as follows. So we see that vertex 1 has 2 neighbors, 2 has 3, vertex 3 has 3 neighbors, vertex 4 has 2 neighbors. And there's zeros where the vertices are not adjacent. So 4 and 1 do not have an edge between them. So we have 0 here and here. All right. So how does the Laplacian matrix help us? So it can be viewed as a Z module map from Zn to Zn. And recall that we define the co-kernel as follows. So if we're given a map from X to Y, the co-kernel is the target mod the image. And then the sandpile group is defined by, you have your co-kernel, and then that is, of course, your target mod, your image, and that's isomorphic to a copy of Z, direct sum, the sandpile group. However, if we just consider the reduced Laplacian, that co-kernel is isomorphic to our sandpile group. And then finally, due to Kirchhoff, we know that the cardinality of the sandpile group is equal to the determinant of our reduced Laplacian, and that's the number of spanning trees of G.
Why is it called the sandpile group?
Oh goodness, I actually have forgotten the actual reason. I think it does have something to do with chip firing, where it models pieces of sand on a lattice, but is any more details than that I've forgotten. So, but it is a fun
Don't
game.
worry, thank you.
So a way to kind of simplify the calculations needed for a Sandpile group is to look at the Smith normal form of our Laplacian. As you can imagine, that matrix graphs can get fairly complicated. So it's nice to just simplify it. And by doing that, we're not losing any information, because all we're doing when we calculate the Smith normal form is we're just doing row and column operations over the integers. Okay, so recall that the Smith normal form of a matrix is a diagonal matrix where the diagonal entries are such that DI divides DI plus 1. This kind of gives you a visual here. All right, and so for our example that we had, that second graph, the Laplacian is actually the matrix with the diagonal entries 1, 1, 8, and 0, and the reduced Laplacian, where we have taken out a row and a column of our original Laplacian matrix, and then we calculate the Smith normal form of that reduced Laplacian as entries 1, 1, and 8. And so this tells us that our co-kernel is isomorphic to Z mod 8Z. So, graphs of interest. So one interesting graph to look at is the cone over the path, also known as an infan. So to make this graph a little bit more accurate, of course, we would have an edge to all the vertices in the path there. So as it turns out, if we have a path in vertices and a cone over that path, then the Sandpile group is Z mod F2N Z, where F2N is an even entry in the Fibonacci sequence. So recall the Fibonacci numbers, where we get a Fibonacci number by from the sum of the previous two entries. To prove the above theorem, we used a method similar to that used by Bodingovich for the number of spanning trees in an infan. And because of the structure of our graph, the corresponding Laplacian has the following general form. Okay, so this entry here corresponds to the neighbors that the cone vertex has. So of course it has n neighbors. And then the vertices that were formerly leaves in our original path have 2 neighbors. The other vertices in the path have 3. And then the adjacencies are described by the -1s and the 0s. But it has a very standard form, so that we have -1s in this first row here, this first column. Besides this A11 entry, we have 1s along the subdiagonal and superdiagonal.
I'm a little confused. In this picture, 1 has n-1 neighbors, isn't it?
Oh no, so there's n vertices in the path.
Oh, then.
Yeah.
Then it should be an n+1, I guess. The last label.
Oh, which one are you?
But
I see what you're saying. Yes, yeah. So maybe I should have, just labeled the graph differently. Yeah. Sorry.
Okay.
I was trying to keep you on your toes right there, like, oh. But no, you are correct. Yeah. Also,
Okay.
I feel like I need to be a little better with the graphics, because there are obviously several edges missing. So, but all right. So the claim is that the Smith normal form for our Laplacian matrix of such a graph has the following structure. Okay, so we have ones along the diagonal. We have our entry from the Fibonacci sequence here in the second to last entry in the diagonal, and then 0 there. And in order to prove this, we need a proposition, a corollary, and a recursive formula. All right, so recall the following proposition. If we have a matrix over the integers, and it has the Smith normal form as follows, where we have di going all the way through dn. Of course, since it's Smith normal form, we have that di divides di plus 1. Then the product of di through dk is the greatest common divisor of all k by k minor subdeterminants of A. So we'll use that later as well. And then also recall that if we have a square matrix over the integers, then there is a n-1 by n-1 minor of our matrix with determinant plus or minus, if there is such a matrix with determinant plus or minus 1, then A has a Smith normal form as follows. So we have ones along the diagonal, and then that very last entry in the diagonal is the determinant of A. All right, so for our particular matrix, observe that we have an n-2 by n-2 minor. It's an upper triangular matrix, so about 1 to the diagonal. And that has determinant 1. And so we have our Smith normal form that has 1 along the diagonal, and then a value x here, where x is the determinant of our n-1 by n-1 submatrix. And now it just remains to show that our x is actually that number from our Fibonacci sequence. So we take our reduced Laplacian matrix, and then we do cofactor expansion, and we label each minor. Okay, and then we observe that we have a recursive formula that exemplifies our sequence. So we have our reduced Laplacian, we take that determinant, and then we do the first cofactor expansion, gives us 2 times bn minus 1 minus a minus 1, determinant of bn minus 2. Okay, and we're just determining the determinant in the usual way. So we have an equals to bn minus 1 minus bn minus 2, where they're labeled as above. And then as we're explaining the cofactor expansion, we end up with 2 times 3 bn minus 2 minus bn minus 3 minus 3 bn minus 3 minus bn minus 4, ending up with an equals 3 an minus 1 minus an minus 2. And then as it turns out, entries in the Fibonacci sequence that are indexed evenly, they actually satisfy the same recurrence. So we have f2n, and that equals a sum of f2n minus 1 plus f2n minus 2. Okay, we can substitute how we obtain f2n minus 1 by the following next line here. Well, the first term of this next line. Okay, and then with a little bit of algebra on this line, we finally obtain that f2n equals 3 f2n minus 2 minus f2n minus 4, which is what we wanted. So with that, we have that our x value is our f2n, and so our co-kernel which is the determinant of our reduced Laplacian, is Z mod F2N Z, which is awesome. The next result is for cones over stars. So here, the configuration is slightly different than you might expect, but if you, so if we kind of ignore our cone vertex, you see that we have a star here, we have a center vertex, and all of our other vertices and edges as we would expect. If we add our cone vertex, we see here that we have 2 vertices that are adjacent to every other vertex in our star. So if we have a star on n-1 vertices, and our graph is the cone over that star, then our Sandpile group is Z mod 2n to the n-4, direct sum Z mod 2nz. So similar to before, we're just looking at our degree matrix minus our adjacency matrix. So I've labeled the cone vertex as 1 and the center of the star is 3. So we have that first vertex has n-1 neighbors, the third has n-1 neighbors. And then we have 2s along the diagonal besides the entries corresponding to vertex 1 and 2. And the other adjacencies denoted by the -1s. And then inductively, we can prove using row and column operations that the Smith normal form has this general form. So we always have n-4 number of 2s in the diagonal of the Smith normal form. The A in n entry is always 2n. And so from that, we can deduce that the Sandpile group is Z mod 2n, n-4, direct sum, Z 2n. So those 2 results were actually pretty exciting for me. The stuff that I'm looking at with my advisor is the following. So conjecture 1 and conjecture 2. The question is, if we have an arbitrary tree and then we take the cone over that, and then we look at the star and the path, and we take the cones over those, is the Sandpile group of an arbitrary tree bounded by the Sandpile group of the other 2 graphs? And then if I look at the type polynomial of those same graphs, is there a way that we can look at the coefficients of the type polynomial and actually bound the that type polynomial for the cone of an arbitrary tree when we're setting x equal to 1? So that's what I've been doing lately. And here are my references. And that is all. Thank you very much.
Great. Let's give Dorian a round of applause for that nice talk.
Thank you.
Great job. Okay, so does anyone have questions? Oh, wait, keep your slides up. You might have-
Yeah.
I think I did. This may have been covered earlier and I may just missed it, but when you take a cone over a graph, when you cone a graph and then you take its reduced Laplacian, would that just be the Laplacian of the graph before you coned it? Because you delete a row and a column, and so you just always delete the cone vertex?
So the question is the Laplacian, the reduced Laplacian the same is if I just got rid of the cone vertex. Let me look here, think about it.
Wouldn't it change?
Oh, sorry, what were you saying?
No, you go, Dorian.
I think not quite, but I'm kind of having a hard time thinking on my feet right now.
I
But-
think that what people are saying in the chat, which is that the degree of all the vertices changes when you have a cone point. So then like the entries on the diagonal would also change.
Oh,
Right.
that does make sense.
Right, because yeah, no, a path graph should not have any vertices of degree 3. So if I just delete a row and a column. Okay, thank you. I was also having difficulty doing it in my head, which is why I asked.
So thanks for the question. Sorry, I probably I am not able to see the chat, so I probably. Is there anything else in the chat? Sorry. I don't have that. Nope.
There was a good question earlier about whether because like your Sandpile group for the path is like counted by the Fibonacci numbers. Vishal asked, I wonder if there is any connection with tiling the path graph with dimers and monomers, as that is also given by Fibonacci numbers. And then Vic said, could be. Certainly the recursion she uses to compute the determinant of the reduced Laplacian will be similar to recursions that count the dimer and monomer.
Awesome. Yeah, I don't really know much about, yeah.
So I have one more remark. Can you go to the inequality at the end?
Yes.
Yeah.
You said go to the very last slide here.
With the Tut polynomial, yeah.
Okay. Mhm.
Yeah, I remember seeing I can't recall exactly, but I remember seeing somewhere that some specializations of the Tut polynomials have particular combinatorial interpretations in terms of graphs.
Yes.
So I think T1 comma, I'm not sure if T1 comma Y has, I think it does probably. So if you could, I was just wondering if you had, if you were aware, if you had looked into that or.
Oh, yes. So the Tut polynomial, when we're setting x equal to 1 and just looking at y, that is looking at the external activity of the graphs. And then when we set both x and y equal to 1, then that actually calculates the sum of those, that calculates the spanning trees, the number of spanning trees.
Okay. Yeah.
I don't know, was that what the question was, or?
Yeah, I mean, just a remark. I was just wondering. So I remember there was some work done by Olivier Bernardi on some of this stuff a while ago. But yeah, not really a question. I was just wondering.
Oh, okay.
Yeah. Okay, thank you.
Oh, thank you.
So there's another question in the chat. Why are the Sandpile groups of cones interesting compared with general Sandpile groups?
So at this moment, I haven't really been able to compare the Sandpile groups of very many graphs. So I know that it hasn't really been looked at as extensively. So that's one reason why I'm looking at it. But as far as like the comparison of like different graphs, I'm still learning about that. So
I think, for example, like trees have like like trivial critical group if they don't have cones, right? So it's sort of like a more interesting to look at the cone than just the tree. Or
Oh,
the
yeah.
cone over the tree.
Well, yeah, definitely more interesting. I mean, plus it's already been done and looked at, and yeah.
Okay, so there are some more questions in the chat. Dorian, can you see them or do you want me to read them?
Sorry, I should just.
I think it was resolved, but there's a good question.
Okay, I'm looking at the chat now. Okay, so it's possible to resolve by the, oh yeah, Vic answered that one.
Let's have a remark. This is, a new direction relative to what you presented, but it might be interesting to, look at the critical configurations, for these graphs, and try to relate them to try to relate them to the the results on the size of the Sandpile group. No,
Oh, okay,
as
what was the suggestion again? I'm sorry. I will.
To apply the Sandpile, called the toppling operation in the original conception of the Sandpile group, where some of the assignments of non-negative integers to vertices are called critical,
Mhm.
and the number of them is equal to the size of the Sandpile group. And so I'm just suggesting that it might see interesting structure in the in the set of critical configurations.
Okay, so yeah, just look at the set of critical configurations in relationship to the Sandpile groups.
Yeah, I see Vic put a note in the chat to me. Someone's done that for a star graph. Yeah, thanks.
Also, if anybody has any, I can put my email in the,
Yeah.
and if anybody has any suggestions for papers, that would be kind of helpful. Let me just put that in there. Be much appreciated.
Yeah.
Great, thank you, Dorian. Does anyone else have questions? Or comments, suggestions? All right, let's give Dorian another round of applause for a great talk. And I guess we can now stop the recording. And then if people want to ask questions off the record.